I'll be presenting on the findings from this paper that I wrote with my co-author, Mar Hakim. He's pictured here. Just to start, I'll give some background on what are partial differential equations and how do we solve them, just very quickly to give people an idea of sort of what has been done before machine learning sort of entered the field. This is an example of a partial differential equation. It's called the advection equation, and it relates the partial derivatives of time with respect to space. Now, for this PDE, this partial differential equation, we know the exact solution. So the exact solution just says that if your initial condition looks like this in blue, or it looks like anything, the exact solution is going to translate to the right with a speed of 1. And so after 2 units of time, it's going to look like this thing in red. And so we know the exact solution here. Now, normally you don't know the exact solution, and you're going to need to use some sort of algorithm to come up with the exact solution. But what we're going to do is we're going to look at one type of algorithm that you could use to solve this equation, which we already know the answer for, just to illustrate sort of what people do. And so the algorithms that people use generally follow sort of a 3-step process. That's not always true, but this is sort of just to simplify. The first thing you're going to do is you're going to discretize your equation. And so if my initial condition is this blue dotted line, in this case, I'm doing what's called a finite volume method, which is where I divide the region into domains, into volumes, and then I represent the solution with an average within the domain, within each volume. And so that's just the integral of the solution. Then I'm going to integrate the integral of the initial condition. Then I'm going to integrate the equation, and I get an equation for the time derivative of each of the cell averages. The third step is going to be some sort of approximation. So after you've integrated the equation in some way, you're going to approximate in some way. And the details here aren't super important, but basically we can see that different choices of approximation scheme are going to get you different levels of accuracy and different sort of qualitative characteristics as well. So this is what are called numerical methods, or what we call standard numerical methods, because they're the standard way of solving PDEs. Now, enter machine learning. There's been a lot of interest in using machine learning for research related to PDEs. And there's a couple of different areas. This review paper from Brenton and Cutts sort of breaks down the research into sort of 3 different areas. And the one we're focused on in this paper is called what we call forward problems, or well-posed boundary problems, which is basically solving a PDE. So given the PDE, can you learn to solve it accurately and efficiently in the same way that numerical methods do? Now, this isn't the only area of research, I should say, but this is the one we'll be focusing on. And just really quickly, this is a big research area. So for example, if you go to the Journal of Computational Physics, they publish a lot of research into PDEs and numerical methods. And you go to their most cited papers or their most downloaded or whatever, they're all papers that you can see. These are all machine learning papers. They all relate to neural networks in some way. And so this has really become a really big area of research in the PDE community. Part of, I think, my dissertation topic was to understand what is going on here, what has been useful, how can we apply this to the research in our field? Why is there so much interest in this? As I was doing my PhD dissertation, my advisor and I sort of identified 2 issues that were quite common, and I'll talk about what these are. The first of these is weak baselines. So weak baselines are not new in machine learning by any stretch. So for example, there's this famous paper from 2009 called Improvements That Don't Add Up. What they say is that basically what this is reviewing the field of information retrieval over the past 10 years. And what they do is they have this contest in 1998 on a standard benchmark. This is like an MNIST of information retrieval. And the black line was the best result achieved in 1998. This was the 75th percentile of results in 1998, and this is the 50th percentile. Each year, as we go along the x-axis, people are publishing papers in information retrieval in these conferences and on this benchmark, and the X's are the baselines that they use, and the solid circles and squares and triangles are the results they get. And so you can see that most of these papers have an improvement over the baseline. So all these papers are saying we introduced this new method, it does better. However, because all of the baselines are weak and many of them are none of them are better than the best in 1998, and many of them are actually worse than the median in 1998. Despite all these papers claiming to make progress, actually no one has done better than in 1998. So this is sort of analogous, I think, to what I'll be presenting on in this section. Just sort of an analogy to see that this is not a new phenomenon. So what is a baseline? I think we're all familiar, but just in this context, if I create a system to solve a PDE using some data, loss functions, etc., I then, once I've trained it, I want to evaluate the performance of that model. And so to evaluate the performance, I'll have to compare it to something else. This is standard in machine learning, and what I compare it to is called baselines. Now, I can compare it either to the standard numerical methods, like we saw at the beginning was an example of one, or I can compare it to other machine learning-based solvers. In this talk, I'll be focused on comparisons to standard numerical methods, and not people who compare one machine learning model to another, although it's possible some of these issues exist there. It's probably likely. Over the course, sort of as I kind of alluded to, over the course of my PhD dissertation, Amar and I became concerned that there were comparisons to weak baselines leading to inflated performance claims. So we decided to study this more carefully. And so what we did is what's called a systematic review. This is a common technique in, for example, medicine, where you're trying to sort of use all of the available evidence to answer a question. And so what we did is we searched for every paper we could find in the literature. And I won't go into how we did that process, but basically we found 82 papers that matched three criteria. And the three criteria were that they use machine learning to output a solution to a fluid-related partial differential equation. They compare performance to a standard numerical method baseline, and they're available before a certain date last year. So I should say that this means that the results here don't apply to inverse modeling. They don't apply to weather PDEs, not weather PDEs, weather systems, climate systems. They don't apply to quantum mechanics PDEs, solid mechanics PDEs, et cetera. So I wouldn't assume that these issues apply to all areas, but some of these areas might suffer from similar issues. And then we're also, again, not looking at ML baselines. Okay, and so of those 82 papers that match these criteria, we find that right away that the vast majority of them claim to do better than their baseline in the quantitative metrics they're looking at. So as we can see, it's quite rare in this sample for papers to do worse than their baseline. So there's a lot of optimism in this literature. Then the research question we wanted to ask was, of those 76 articles claiming to outperform their baseline, did they make a fair comparison with a strong baseline? Okay, so what does it mean to make a fair comparison with a strong baseline? So we saw two pitfalls that were really common in these comparisons, and as a result, we introduced two rules that must be followed for a fair comparison. And these are necessary but not sufficient, but they're the rules we use to evaluate. So rule number one is to make comparisons at equal accuracy or equal runtime. So what does that mean? This figure here is a figure from a paper by some researchers at Google. It's a really nice paper, and they do actually a great job of following rule number one. So in the x-axis, they have accuracy. So higher time until correlation is higher accuracy. And the y-axis, they have runtime. And this blue method is a standard numerical method. And we see that there's a trade-off between accuracy and runtime. So if you want a more accurate solution, you have to use more grid points, and that takes more time. And then what they do is they have this machine learning model they train, and they see that at a given accuracy, they have their faster speed. In this case, they're 86 times faster. So that is a correct way to follow rule number one. What they do is they look at constant accuracy, and they compare this red point here to this line here. Now, what would not be a fair thing to do would be to compare this blue dot here to this red dot here, and say that they're 4 orders of magnitude faster. You can't say that it's 4 orders of magnitude faster because this point is very accurate and this point is much less accurate, and you can reduce the resolution to make the standard numerical method baseline much faster as well. Rule number two is a little simpler. It's basically just saying that some numerical methods are going to be faster than others. We replicated this figure on CPU. So it's not like a one-to-one comparison, at least in this figure. We also replicate on GPU. I don't have that plot. And what we find is that certain methods, such as the pseudospectral method and the discontinuous Galerkin, are going to be orders of magnitude faster than this finite volume method, especially the pseudospectral methods. Yes, the machine learning model is faster, but there are also numerical methods that are much faster. And so if your goal is to be faster, you really need to be comparing to the fastest numerical methods. Otherwise, it's not a fair comparison. So we introduce those two rules. We evaluate them for all of the 76 papers that claim to do better than their baseline. So what do we find? Okay, so here are the first 15 papers. We've ordered them in number of citations. What we can see is that, first off, most of these papers, their sort of primary quantitative outcome, they're claiming that the machine learning model is a lot faster in most cases than the standard numerical method, and sometimes by many orders of magnitude. But what we see is that in most of these papers, either rule 1 or rule 2 is not being followed. And as a result, because at least one of the rules is not followed, the comparison is not fair for most of these papers. Here is the second part of the table. Again, we see most of these papers, at least one of the rules is not being followed. This orange sort of caution sign just means we think it's likely that the numerical method was inefficient, but we don't have enough evidence to say for sure because we haven't replicated the result. And that didn't really make a big difference, but it's just worth saying. Here's the next slide from the table. And again, most of them follow either rule 1 or rule 2, but not both. And here is the last. Of these 76 papers, some of them do compare to a strong baseline, 14 of them, but many of them, most of them, 60 out of the 76, do not follow at least one of the two rules, and so are comparing to a weak baseline. Now, another thing we find is that the articles that compare to a strong baseline have quantitatively smaller improvements than articles which compare to a weak baseline, which sort of suggests that the more impressive the result, the more likely the article is using a weak baseline. Now, you might say, okay, does this matter? Is it really a big deal that we're comparing to a strong baseline rather than a weak baseline? And we think the answer is yes. It is a big deal. And the reason that we think that is because in 10 of the cases, we actually reproduced the results using a stronger baseline. And we focused on simple 1D and 2D PDEs and simple geometries that could be easily reproduced. And we found that in every case except for this one, except for number 6, the stronger baseline was at least 2 orders of magnitude faster than the weaker baseline. Using a strong baseline can make a really, really big difference. And in most of the cases we found, it made a really, really big difference. So the conclusion of this section here is because the only possible benefit of using machine learning to solve PDEs is to do so more efficiently, and I haven't really talked about that, but it turns out that that's the case, then these results call into question whether machine learning has the potential to be useful in practical applications, at least related to PDEs from fluid dynamics. And that's whether or not that it has the potential is sort of a long discussion, but it at least calls it into question. The next part, the next issue we identified is called reporting biases. So what are reporting biases? So they're defined as when the direction or statistical significance of results influences whether and how research is reported. So there's a couple, there's a lot of sort of common biases that sort of fall into this umbrella of reporting biases, things like the publication bias, p-hacking, outcome switching, harking, which is hypothesizing after results are known, et cetera. So these are common biases. They're discussed a lot in certain areas of science, a little bit less in machine learning. Just to illustrate sort of what reporting biases can do and how they can cause the scientific literature to be skewed towards over-optimism, there's this really, really nice paper. It's not from machine learning, it's from medicine. What they're doing is they're looking at 105 trials of antidepressant drugs. So these are randomized controlled trials funded by the NIH. If you're going to get funding from the NIH, you have to put your results by law, you have to publish your results in this online database. And so this is every trial for antidepressant drugs that's ever been funded. And it turns out that half of the results are statistically significant and half of the results are not statistically significant. This is sort of a nice sort of test study, or not half, almost half. 53 out of 105 are positive and 52 are negative. So what happens is that of the trials that do not achieve statistical significance, half of those results are not published in the scientific literature, but almost all of the results with positive results studies with positive results are published. Then of the results that publish that have negative results, half of those will do some sort of outcome reporting bias, which is usually basically p-hacking, where instead of reporting the outcome for the sample that they studied, they'll look at some subset of the sample. They'll say for men or for women or for young people, it was statistically significant. So this is variations in p-hacking. And then of the results that still don't have statistical significance, half of those will do what's called spin, which is where they'll use positive language to discuss a result that was not statistically significant. And then sort of to add insult to injury, the papers that have positive results are cited 3 times more than those with negative results. So when you look at the scientific literature, almost everything you see is, wow, these things work, they're statistically significant, but actually of all the trials that were done, half were not statistically significant. And so the scientific literature can be quite misleading as a result of these biases. How positive is the machine learning for PDE literature? So I tried to estimate this. I don't have time to talk about the details of how I did this, but basically I looked at 232 papers whose abstracts mentioned positive and/or negative experimental results. I tried to sample them using Google Scholar. And of those, 95% of those experimental results in the abstracts are only positive. And 5% have some combination of positive results and negative results. It does better here, but it doesn't do better here. And in no cases, none of those 232 papers did the paper's abstracts say, we don't beat the baseline, period. And that was the only result. This doesn't prove that reporting biases are going on, right? But it does suggest that we should investigate them. Now, I don't have a time to talk about all of the evidence of reporting biases I found looking through the literature, but mainly we saw things like, this is by the way, this is a little bit harder to find evidence of than in the antidepressant paper I showed you, because I don't have a database of what was going to be done and what people were planning to do before they knew the results. The things that we did see were, for example, reporting results for one PDE in terms of comparison to a baseline, but then not comparing to baselines for other PDEs. Another thing that was common was, instead of reporting the runtime, which is quite a hard thing to beat for a standard numerical method, they would report different metrics that were easier to beat the baseline, and then not report the sort of standard metric of runtime. So we look at the literature, we see evidence that suggests reporting bias. So here was sort of a natural experiment in the literature. So what we did was we have 2 samples. We have sample A, which are the 76 articles from the table I showed you. And all of those articles in this third column represents what was published in the scientific literature. And all of those articles reported positive results against their baseline, which was a standard numerical method. In sample B, we use 60 articles that all use what I call the physics-informed neural networks to solve fluid-related PDEs. Now, we know that PINs, these physics-informed networks, are not faster than standard numerical methods, but they're not anywhere close for fluid-related PDEs. And so all of these papers are going to do worse than the standard numerical method baseline. But what we see is that in the literature, most of those papers do not report the runtime of the standard numerical method, even though they use the standard numerical method to generate the data. What's sort of going on here due to these 2 issues is that the issues are causing the scientific literature to be skewed towards positivity. So the conclusion here is that when authors have a positive result, they usually highlight it, but when they have a negative result, they rarely report it. That's sort of consistent with what we're seeing. And that's sort of skewing the literature towards positivity. Now, I should say that this left column here is an estimate. I don't know exactly what the results would be if they use strong baselines, because I didn't replicate every paper. So I had to estimate in this table. Okay, so last couple slides, and then I'll take a question. So why is this going on? What's causing this? So to some extent, some of these things I think are specific to the intersection of fluid-related partial differential equations and machine learning. So machine learning, as I think we know, is a very quantitative field. People are focused on metrics like, what is state of the art? Did you beat this baseline, et cetera. The numerical methods community is not really as focused on quantitative metrics. The focus is often on theoretical properties of algorithms and understanding under what conditions does an algorithm give good results, and is it reliable, and what conditions is it not. And so these quantitative comparisons just aren't really being performed in the numerical methods literature. And so the state of the art is often unclear. So that's number one. But then part of it too is that the machine learning researchers who work on these things, and I've been guilty of this for sure, lack domain expertise in numerical methods. So when I first started, I was trying these methods, and I hadn't really had no idea sort of what the space was of algorithms to solve these. And it turns out to be actually quite hard. You need a lot of expertise to know what the right method is, or at least what the state-of-the-art method is for a given PDE. And then the third thing was that I just didn't see people putting a lot of effort into choosing baselines for the most part. People just sort of took what method they knew of or what sort of package they knew of, and didn't realize that actually this makes a really big difference in terms of interpreting your results. Okay. However, so some of that is unique, I think, to this situation. However, some of that I think is more sort of generalizable in terms of what's similar to past reproducibility crises, and really what's actually quite similar to what I showed you with that antidepressants paper. And so I think there's sort of a three-step process going on here. So the first one is that researchers have many degrees of freedom when they write a paper. So, and there's a ton of degrees of freedom, especially in PDE research, machine learning for PDE research. So they might choose, which PDEs am I going to look at? Which ones am I not going to report? What are my boundary conditions going to be? What are my initial conditions going to be? How am I going to choose my diffusion coefficient? What baseline do I want to choose? Do I want to, compare what metric do I want to use to validate? There's all these choices that you make. That's inevitable in any paper in this area. However, what happens is that those decisions about analysis and reporting are made or altered after results are known. So you have the ability to have the results influence the way those results are reported. And then the third step is that because there are these perverse incentives in most of science, but I think especially in machine learning, the conditional probability distribution of each of these decisions, given the experimental results, tends to be biased in favor of positive outcomes. And the cumulative sum of these biased decisions tends to filter out negative results and lead to overly optimistic conclusions.